The blue robot, it's ideal and it's perfect, but it does not exist in the real world. To get to the real world, we need to design it. And we see that with this multicolored robot. And there's a problem, and we need to fix it. Now, the blue robot, it exists on the controller. All right? And there's the blue robot. And the blue robot allows us to anticipate the speed and torque of each of the motors that actuate the system. And for our problematic axis, the one that's driven by the motor we call the forearm motor, we see what we're asking it to do in terms of speed, and a top speed a little bit more than 1 radian per second, and a top, I'll say, amplitude of torque, which is a little bit less than 1 Newton meter. Here's our design. We got the mechanics and we got the electronics, and here's our problematic axis. All right, and you'll see that we use the blue robot to figure out how much torque we need, and we see 1.5 Newton meters should be good. And we certainly are making the speed with a no-load speed of 180 radians per second, I'd say with quite a bit of comfort. But there is a problem, and the problem's right there, that these are values you would get when this motor is powered by a 30-volt DC source. And we'll see that we're only using 10. So the fix seems easy enough. Just make that a 10, right? So that's actually a huge change we just made, because it really means let's change it with a different motor, right? And so what it really means is we're able to generate 1.5 Newton meters with a 10-volt source now. And so in effect, we're really applying a motor that's probably 3 times more powerful. So let's see how we do. And we see we do very well. So here's that DC motor, resized, capable of delivering voltages and currents that can drive the torques, and adjust the torques to achieve the movement that we need. Okay, for a number of reasons, there are a lot of real good reasons, people really like PMSM. So here's a PMSM motor from Simscape. It's a 3-phase voltage one, meaning it's got 3 terminals, A, B, and C, where we apply voltage. And that this is all achieved because there's this remarkable thing called field-oriented control that does the calculations to operate the, I'll call it the voltage controls, to deliver those voltages to that motor. You'll see that it delivers these real nice sinusoidal waveforms, at least once the motor reaches a constant velocity. And we'll see that for both voltage and current. All right, so let's copy this, paste it in. Let's match the size, and let's replace this. Adopting conventions for interfaces to Simulink blocks is a really useful thing. All right, so this AC motor working with these DC motors still kind of operates against that same user interface, and even in its description, let's go ahead and put in a similar description. Put in 1.5 Newton meters for the stalled torque. Let's put in 180 radians per second for the no-load speed. And in general, you accept what the motor vendors tell you, or we should go and test these things. But you know that these are not really design parameters, but these are really just kind of what it takes for a motor to deliver on, kind of torque and speed requirements, right? And generally, motors are the 4-pole pair. And again, very importantly, let's put our voltage rating at 10. And let's see how we do. And we'll see that the use of the PMSM leads to these very interesting waveforms for both voltage and current, where all 3 A, B, and C circuits are tracked right here. Which leads to success as well. So a goal of this video and the collection of videos I'm recording right now on mechatronics with MATLAB and Simulink is to really emphasize how important knowledge of the robot is, knowledge of what it is mechanically, how important that is to choosing electric motors as well as operating through feedback controls, the software that runs the robot. And so anyways, putting this on the controller is quite important. And just to kind of reveal more fully that there's actually a third robot, and we'll save this for another video, but that same robot can provide for us the inverse kinematics to make sure we get those motor angles correct to make the robot move the way we need to. Thanks for watching.